So this thing's very simple. It's a huge simplification of the real problem. It's only got this action and this reward, yet it still has a fundamental trade-off that you have to kind of explore. And this epsilon greedy action selection is kind of the simplest way to do that. But you still have to learn, in order to learn those action values, that's how you build up this model that lets you do it. So in the book, they have a bunch of experiments to show actually running this on something with 10 bandits. And so here we're literally having this example where we've got 10 bandits up in a line at, let's say, Casino Niagara, not Las Vegas. It's going to be smaller. Well, even Casino Rama, maybe closer to home if you're in Waterloo. Is there a casino in Waterloo? There must be. Casino Rama is still pretty far. But basically there's a line of these 10 machines, you got to pick one, and they have an inherent distribution, right? So we're saying that the reward distribution of these that we do not know is, what is it? Some number. This does not give you the number specifically. Q5, Q5, Q2. Yeah, so the actual number's not given, but we can see the distribution here, right? So in this one, for machine 4, the mu is like 0.7 or something like that. And they've all got variance of 1, standard deviation of 1. Some of them, this one, its mu is more like, sorry. This one, its mu is more like actually close to 2. And so then you don't know this, what the distributions are, but as you take actions, you can kind of try to estimate it, right? And so in their experiment here, which is what they're showing, they run this for 1,000 steps, and your agent uses the above policy algorithm that we talked about and tries to run its policy, picking the best one and then randomly picking the wrong one and learning and updating its counts and building an estimator, right? And so we can see by this, if we know that the best action to take is 3, 3 always gives you the highest reward, but sometimes it might give you a bad one, right? So sometimes you might have been better off picking this, right? So you could have some policy that maybe, you know, mixes these together early on if you're not sure yet, and that would be a really good policy. Any policy that uses 6 would be a pretty bad policy because it's bad. You're going to lose. The results they're showing here are of saying that, and this is a good example because it shows you how much computation you have to do even for a very simple system like this, right? Because these have no state, they're just a bunch of Gaussians. So you're going to run it each time you play. You're going to start from scratch. The agent knows nothing. You set Q and N, the model, to 0, and you start from scratch. It's basically a blank slate. And then reset, and then do it 1,000 times. That doesn't make any sense. And then learn something and you get your result, how well you did. And then do that whole thing 2,000 times again to see if you can improve your estimator. And so what are we seeing here? This is our first example of a reward graph, which you'll be seeing a lot of. And so this is kind of the main way to report results in reinforcement learning. There's other ways that can help you improve it and try to see different variations of it, but the fundamental thing you want is you want to say, what's your reward over time? It could be average reward or other types of reward, but some measure of how much money you're making or how much value you're getting over the number of steps as you learn, right? So starting from nothing, starting from no knowledge, which is what we mean at 0, and running forward so many steps, how well do you learn? How fast can you learn? That would tell you kind of how good your algorithm is, right? So what are we seeing here? What we're seeing are 3 different graphs, and we said we ran it 1,000 steps, right? And then we did it 2,000 times, so we're averaging all the different values. Pretty sure that's what they did. It's the average of 2,000 runs with this setting, right? With this setting. So, right, so remember it's epsilon greedy, right? And we've got 3 different values of epsilon. We've got epsilon 0, epsilon 1%, and epsilon 10%, right? And remember, if you have that policy, we're going to pick action is going to be, argmax, picking the best possible value of A with probability 1 minus epsilon, and then picking something else with epsilon. Right. So 1 minus epsilon means almost always, right? So epsilon equals 0 means that 100% of the time you're just always taking the greedy one, right? So whatever you started with randomly, you eventually stabilize and you stay with some particular policy. If you say 1% of the time you're going to not pick the best action according to your model is going to keep slowly improving, right? And 10% in this case improves even faster, although you could wonder whether at some point they're going to cross, and they probably will, because the lower number is usually going to do better at finding all the nooks and crannies, and that actually relates to local optimum that someone was saying before. The closer you are to 0, the probably better you are in the very long run. We've already run it 1,000 times 2,000 just to get this data, so it depends how long you have. So why does epsilon greedy even get to this point? Epsilon equals 0, get there, right? Can we understand that? Do you understand what I'm talking about? Like, this is a problem. If we think about Q started off completely randomly, right? Yeah, that's right. Right. So it's just using the values that it got randomly as like Q. Well, actually, we set in this version we said Q equals 0 for all A, right? The Bellman equation saves us all. Yeah. But initially, it's so wrong that all of them are going to be equal, right? So at the beginning, if you're picking the one that's maximum, you're going to get some exploration just by default, right? So there's explore here, even with epsilon equals 0, because initially they're all 0, right? And so you'll pick one that's 0, and then you'll lose money on that machine, and then you realize some other one is 0, which is better, and you try that. Right, so you keep trying all the machines until they stabilize to the point where one of them is better than all the others, right? Because if you think about what can happen is, like, imagine you were playing this game, and this is the actual distributions. If you happen to pick this guy first, you're like, okay, great, and I won something. You're never going to lose money on this bandit, basically, right? It's almost impossible to lose money. You have to be very unlucky. Right. So if you happen to pick this event initially, you'd be good. But what if you picked this one first, right? And you found it was really good, and the first few times you picked it was here, and the first few times you picked, well, the first time you picked 3 even was here. Now you've got a value, say, okay, I got 1, that's my value for this guy. Here I got 3, so that's better. Let's just say that we only even get them once, right? So we got a value here. When we pulled this, we got here. Everyone else who got something where they are, you'll stop, right? You'll never get better than this. You'll say, okay, that's it. Because there's no exploration. You just say, once I have one that dominates everybody, I'll just pick this. In fact, if you got 3 here, you'd never try anyone else because all of these were initially 0, right? The only reason you might explore around is that some of the times on the first run, you're actually going to get negative values. And so 0 still looks better than negative, right? So all of this exploration comes from getting away from 0. And once it gets to something, it stays there. And the variation comes from the fact that it was run 2,000 times, right? So it's a good average. It just stabilizes at a reward of essentially 1, which I guess is not surprising because most of them have something in 1, depending on which one it picked. Right? Whereas if you add a little bit of space to say, okay, we're going to go off script and pick something suboptimal, over time you will eventually find out that that Bandit 3 or Bandit 6 are much better, and then you'll start using them. Right? And the more randomly you let yourself explore, the faster you might learn that. Then the other part to try to explain is why this happens, that, I should switch colors, sorry, that it's so slow to converge. You can think about how, and we'll see more examples of this in other methods. We think about how we're converging to something more realistic by seeing more variety. So because the advantage of this Bandit domain is that it's so simple, we can actually compute the optimal solution. So we could set this up as an optimization problem with those distributions, since we do know them, and say, well, what's the actual optimal policy here, given these, how much would you get if you just pick the one? Well, I mean, in this case, we know it's 3, so we should just pick 3. Maybe it's a randomization amongst these. But you can optimize the probability of these and say, what's a weighting amongst the top ones to give you optimal expected value. And so we can plot the same thing, but with respect to what your reward is relative to how much you'd get if you were just following the optimal policy every step right from the beginning. So the relationship is the same. They're really the same curves. The scale is different, but it gives you a sense of how far away you are and how bad not being greedy is, because you're not even getting 50% of the value of the system. Oh, okay, that was where that thing stopped. Okay. Okay, so any questions? Okay, we had another question there. It's the average reward 1 for epsilon 0, simply due to the distributions. Looking for the Bandit says there's no special meaning to conversion to 1. Yes, no, I was wondering about that myself as I'm looking at them. Yeah, 1 is not any particular thing here. It's just that it must work out that we'd have to write it down. And if you look in the textbook, they have more detail about this test bed. So we'll check there and see. But I think that's just the steady state expected value, right? Because a bunch of them overlap there. Because you are still updating it to try to improve yourself, right? So from this initial exploration, you are still more likely than not to find at least one of these higher up ones, because anything negative, you will try 0. So you would expect that the thing it converges to is, given this distribution, that it will converge to something greater than 0, because if anything ever gives you negatives, you always could have picked one of the zeros first, especially since some of these guys hardly ever have 0. So you would find your way eventually to one of these things that's largely above 0, and then you'd be averaging amongst those, and you'd basically stop doing these almost ever, right? But that's kind of because of the luck of us initializing everything to 0, and the way these distributions fall out. It could easily be a different number. So you're right, yeah, 1 is not special here. Yeah, and the way you break ties, as someone's asking, is that's very relevant, is relevant. So in our code here, break ties randomly. Yeah, so you have to have a rule to do that. So you could say break ties randomly, or you could break ties based on previous things you haven't tried. There's some ways of setting these up so you actually assume, so like an alternative way, which is actually very effective. We'll talk about it again at another time, but instead of setting Q to 0, what if you set Q to infinity for all of them? Right? This is called an optimistic model, an optimistic initialization. Sorry, I'm misspelling. If you set that to infinity, then that says, I don't know what the value of this arm is, but I bet it's great, right? So you've never seen the value of it, so you assume it's very high. And that has the advantage of being that you'll be wrong all the time at the beginning, but it means you'll try everything once, right? Where we set it to 0, we may not try things once at all. Once we find some positives, we may just never try these guys. And that's fine, but it could be that there's one that's better that we never saw. Where if you set them all to infinity, you're going to try them all. Because no matter what you learn, once you get more sure about even the best one, you can say, but what about 2? I bet 2 is amazing. I've never tried it. And then you learn very quickly that it's not. So the optimistic setup is actually very useful in a lot of ways because it forces you to learn and explore the space quickly. And you learn quickly either that things are good, that they're bad, first of all, or that they might be good. And then you still have the long slog to learn which ones are really good. But this risk of missing things is important. But that gets back to me saying how you break ties is important too. But randomly breaking ties is perfectly good.